So the subject of the lecture is angular momentum. I start from the orbital angular momentum, which in classical mechanics is defined to be the vector product. The symbol denotes the vector product of the position with respect to some origin and the momentum of the particle. The origin is important, okay? In general, you change the origin and the angular momentum of the particle changes. Okay, then I wrote the three operators, okay, Lx, Ly, and Z, that are obtained by interpreting this X and P as operators, so X and P quantum mechanically. And I obtained these three objects, which obviously have heads, they are operators, okay? And then by remembering that X and Px is equal to I H bar, and similarly Y and Py, Z and Pz, while X and Y commute, X and Z and Y and Z commute, you can actually calculate rather easily this three commutation relationship between the three components of the angular momentum. Okay, this was the point where I stopped. Okay, so you can condense if you want. Sometimes you find in the book, and therefore I just tell you. Suppose that you denote by alpha and beta any two Cartesian indices, and you want to know the commutator of this thing. So it's I H bar. Then, if the two indices are different, okay, you get the third possible index. So the rule is the following: this object, which is called the totally antisymmetric tensor, is different from zero only if the three indices are different. For instance, X, Y, and Z. All right. Okay. Y, Z, and X. All right. Okay. And then there is a convention on summation of repeated indices. You see here, I'm really, this thing should be written as sum over gamma of this same object. But there is a convention that whenever a symbol repeats, you sum over. Okay? So this object is essentially a plus or minus one. It is plus if the three indices are in this order. Okay? X, Y, and Z, Y, Z, and X, Z, X, and Y. It's a plus. It is a minus if you do a permutation. Okay? So for instance, if you consider epsilon, Y, X, and Z, so you have permuted these two things, that's a minus sign. Okay? So you can work out easily the fact that indeed these three things are simply the three, this object in particular gives you this result. This is also useful in classical vector product of two classical vectors. Okay?
Sorry.
Yep.
In this cyclic method, if I move back y, x, and z, it's a negative. But what if I go y, z, and then go back to x?
Y, z,
Oh,
x.
oh yeah.
Okay. Yeah. I have to experience a little bit because it's simple but can be tricky. Okay. Good. Okay. Good. Now, now I want to change variables from Cartesian x, y, and z to spherical orbits. Okay. You know very well what is the change of variable. Okay. The change of variable is realized by the fact that if this is the x, the y, and the z-axis, to tell me what is x, you can tell me the distance from the origin, call it r, and then you tell me, essentially, this is the projection on the xy plane, you tell me two angles. One is this angle here, and another is this angle here, okay? Which are essentially the latitude and longitude in this sphere of radius r, okay? Good. Now, this is usually called theta, and this is usually called phi, okay? Now, given a point, the x-coordinate of this point, you see pretty easily, is r times the sine of theta. So this is r sine theta, right? Is it clear? Well, this is r cos theta, because theta is this angle from the North Pole somehow, okay? From the z-axis. So r sine theta times the cosine of phi. Okay? Y is the same r sine theta, but it has a sine phi. And z, well, z is simply r cos theta. Is it clear? Okay, well, no. This is just changing variables. Now, what I want to do is now to change variables in remember that somehow this object here is minus I h bar, the gradient operator, right? So x, you change variable from Cartesian to polar in this way, but there is also a change of variables in the p, in the derivative, which is much more annoying. Obviously, you can just go and look with Google, for instance, what is the expression of the gradient in spherical coordinate. Any book in electrodynamics has it, because you have to change variables, I mean, depending on the geometry. But I want to teach you a way of doing it, okay? Which somehow, at a certain point, is useful and instructive, okay? So let's try to do it, okay? So if I have a sum function, okay, of the position, okay, and I tell you, take a derivative with respect to r of this function, okay, you might say, okay, what I need to do is to apply a chain rule, okay? So this derivative of the function is equal to the derivative with respect to x of the function times dx in the r, plus derivative with respect to y times dy in the r, plus the derivative with respect to z times dz in the r. Is it clear? Okay, this is just calculus. Now, these things here are simple to calculate, okay? Let's see what they are. In this case, you have to take the derivative of this with respect to r, which means omit this. This with respect to r, and this with respect to r, okay? So very simple. And therefore, okay, I would just write this object in the following way. You see, the f plays essentially no big role, okay? It's everywhere. So I just omit it. Okay, good. So this is telling me that the derivative with respect to r is equal to this object here, okay, times the derivative with respect to x, okay, here, plus, so this object here is what? Sine theta cos phi. Okay, good. This times that, plus the y gives me this term, so sine theta sine phi times derivative with respect to y, plus the final term is cos theta. Okay, these are, I'm constructing here a 3 by 3 matrix that I want in the end. For the time being, I have this term here. Okay? Good. Is it clear? Now you do for V in the theta. Okay, same algebra. So I have to do derivative with respect to x. I change here theta. 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 Okay? So let's see the three coefficients, what they are. Take x and take a derivative with respect to theta. The sine theta becomes cosine, right? Okay. So I put the cosine theta and the cosine phi. There is an r, okay? So you better calculate 1 over r, derivative with respect to r, so that this r goes away, okay? I'm actually calculating a 1 over r in front of everything, okay? So I'll get rid of this stupid r, which is there playing no role. Okay, cos theta, cos phi. The derivative of this is still cos theta sine phi, and the derivative of this is minus sine theta. Okay? Okay, good. Now you do the last phi. 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 Okay. Now you realize that when you take a derivative with respect to, well, the simple one is, okay, sorry. Yes. Okay, so the derivative with respect to phi of this is sine theta times minus sine phi, okay? So there is a sine theta minus sine phi. This object here gives you sine theta cos phi. Okay. In this object here, when you take it, gives you 0, right? I'm doing the derivative with respect to phi. Yes, 0. Huh? I am doing wrong things, I know. Okay, this is phi, sine, cosine, phi. Okay, here there is no phi, so I get 0. Is it clear? Good. You see that there is a sine theta everywhere. Okay, sine theta here and here. So I can actually calculate, rather than the derivative with respect to phi divided by r, 1 over r sine theta times that. Okay, so there is an extra sine theta that I put there. Here, here, and here. Okay? In essence, what I've done is the following. The derivative with respect to r, 1 over r derivative with respect to theta, and 1 over r sine theta, the derivative with respect to phi, is a column vector of appropriate derivatives with respect to the polar variables. Is it? Yep.
I think you have to erase this sign.
What?
The sign theta at the.
Of course, yes, yes. I just did this exactly to eliminate this object. Thanks. This is a good test. It means that you are following what I do. Okay, good. Is it clear so far? Obviously, in order to obtain, you see here, I have the components of the gradient. So in order to obtain this, in terms of this, I have to invert this matrix, okay? This looks like an ugly thing to do, right? But this matrix is simpler than expected. First of all, let me write it. Okay, let me write in the following way. This matrix here, okay, is in fact the transpose. So I write it now by column, okay? So what I have is the following. I have sine theta cos phi. Okay, and then I have sine theta cos sine phi. And then I have cos theta. This is the first column. Then I have a second column, which is cos theta cos phi. I'm sorry, this is a bit too small. Perhaps someone will complain. Okay? Hopefully. Okay, I'm simply rewriting this first row as a column, the second row as a column. So cos theta cos phi. And, no, there is something wrong. Sine phi. Okay. And then I have minus sine theta. And the third, which is minus sine phi. Then I have cos phi. And then I have 0. Okay? This is, that matrix is the transpose of this. Well, you might ask, why did you do that? Well, first of all, notice this column vector here is essentially the same thing that you find there, okay, divided by r. So this object is the versor, the unit vector, say x divided by the distance from the origin. Okay? You see, if you divide by r, the distance, this is sine theta cos phi, sine theta sine phi, and cos theta. Okay? So this is the unit vector in the radial direction. In the same way, this object here is the unit. So this, by the way, this vector. Yeah.
This must be xl plus y plus the vector over r.
What?
R vector equal to x vector plus y vector plus the vector over r.
No, I do not understand the question.
You write the r vector equal to x vector over r, but I think it must be x vector plus y vector plus z vector over r.
Yeah.
No, I do not understand.
Yeah, so she's saying that the R vector is there should be combination of all the three vectors of R.
I'm sorry, there is an unfortunately clash of notation. When I write this object here, x as a vector, it means x, y, and z. So unfortunately, x as a vector is also it's a kind of mixed notation. I might use x1, x2, and x3, but I mean x, y, and z. I think it's clearer at this level. Okay. So what this expression is telling me is that this unit vector is simply equal to x divided by r, y divided by r, z divided by r, which means essentially this thing deprived of this factor r in front. Okay. Sorry. Good. The second object, it takes a little bit of geometrical intuition, okay, to notice that is the vector, which I will denote theta hat, that goes in the direction of the meridians of this problem. Okay, they go in the essentially direction in which theta changes. You can verify, for instance, that this is orthogonal to this. Okay? You see, if you take the scalar product of this times that plus this times that plus this times that, you do obtain 0. Okay? Try to verify. There is a little bit of trigonometry behind, but sine theta cos theta is there, but then I have cos square phi plus sine square phi, which is 1. Okay? And then I subtract sine theta cos theta. So the scalar product of these two is actually 0. Okay? And you can just verify that this is indeed a unit vector in the direction orthogonal to the radial direction along along the direction in which theta advances. And similarly, there is another unit vector hidden here, which is this one, which is a unit vector in the direction in which phi advances. You see, it is on a plane because it must be orthogonal to these two. And this, in fact, there is 0 component for the z. And then it is, see, if I picture from above, okay, you will see it's the usual minus sign plus cosine. So if I am somewhere, it is a vector orthogonal to the direction in which I'm going. So try to make a little bit of geometrical sense out of this. And if you do that, you will realize that this is the unit vector phi, which is in fact advancing as phi increases. Okay? So these 3 vectors are now not fixed once and for all. They change with the point. Okay? These are the 3. They are called spherical unit vector. One is the radial one, the other is the theta, and the other is the phi. They are 3 orthogonal unit vectors. Okay? So this matrix here is the so-called orthogonal matrices. You know that when you put 3 vectors orthogonal and normalized, so unit 1 and orthogonal to each other, the matrix that you form is an orthogonal matrix. And you know that orthogonal matrix, so such that O, let's call it O, OT is equal to OT, O is equal to the identity, okay? Which means essentially, this is totally equivalent to saying that the inverse of O is equal to the transpose, okay? So if I ask you to calculate the inverse of this matrix, well, there it is. It's simply written there because it's the transpose of that matrix. Okay? Good. So this essentially tells us that the gradient can be calculated. Okay, so let me just write it better now. So so here I have the dx, dy, and the dz is equal to this times, let me just get rid momentarily of this, times what? Derivative, I need to get rid of this, otherwise it's too messy. Okay. Times the derivative with respect to r. I'm inverting this thing. Okay. 1 over r, the derivative with respect to theta. 1 over r sine theta, the derivative with respect to phi. Okay. So this is the expression for the gradient written with this matrix here, and the derivatives with respect to r theta and phi. Let's write it more compactly. First write it, and then we see why this is so. The usual gradient is equal to the unit vector along r times the derivative with respect to r plus unit vector with respect to theta times 1 over r, the derivative with respect to theta, plus the unit vector around phi times 1 over r sine theta d in d phi. Okay, let's see why this is so. Look at the first component, for instance, this one. Okay, it is equal to the first component of, remember that this is r, this is theta, and this is phi. Okay, so it's the first component of r times d in the r plus the first component of theta times 1 over r d in d theta plus the first component of phi, 1 over r sine theta, the inv phi. Okay? So the first component of this involves the first component of this, and that. Second component, same story. Okay? So you see that component-wise, these three vectors are the same. Okay? So this is a compact way of writing this 3 by 3 matrix relationship. Is it clear? Never mind for details, cosines. It's important that you understand that I'm essentially changing variables in the derivatives. And what I got is this relationship between the Cartesian gradient and the derivative with respect to r, theta, and phi. And now comes the beautiful part of the story. This is a bit boring. I mean, no way. Now, L as an angular momentum is equal to what? Is equal to the position operator, vector product with the gradient operator essentially. So minus IH bar, let me put the minus IH bar in front, okay? The gradient operator. Is it clear? This is essentially the definition. And now you realize that x, remember the discussion we had before, x, this object here, is equal to the distance from the origin times the unit vector in the radial direction, right? So when you take the vector product with these three objects, what survives? Do you think that this term survives? Because r, vector product with r gives you 0. Okay, so let's do the rules. R, vector r is equal to 0. What is r, vector theta? Let's see. R, vector theta gives the other one, right? Okay. So this will give you phi. Okay. Oh, wait. The order, let's see. Suppose that this was z, x, and y. So z, x, yes. Okay, that's the correct thing. It's like the usual x, y, and z, but it's simply. And then I have the third one. Yeah.
So you want to change the form.
Oh, yes, this one. Sometimes I write it like this, sometimes the other way. Okay. Good. And then there is the third one, which is R, vector product, the phi, okay? That is equal to minus theta. So if you use these three little rules, you will realize that this object here is equal to, now let me erase this. It's equal to what? Let's see. It's equal to minus I h bar. There is a factor r, okay? And then I have r, this goes away. This gives me a phi, so 1 over r d in d theta times the phi vector, okay? And then I have plus r dot phi is equal to minus theta 1 over r sine theta d in d phi. Is it clear? And now you see that the r goes away. So this is the nice aspect of the story. If I were to ask you, do you think that the angular momentum involves r or only theta and phi? Maybe you would suspect that it involves rotation, so theta and phi, and not r. But this shows immediately why this is so, okay? So R dramatically drops out. Okay, so the angular momentum operator is purely expressed in terms of theta. Phi does not appear explicitly. Derivative with respect to theta and derivative with respect to, well, no, I'm wrong. Really, theta and phi also appear in these two vectors. Okay? Okay? Good. So you can write it explicitly and you will find that the three components of Lx, of Ly, and of all z do not involve R and the derivative with respect to R, which is something very, very nice. Okay? Yeah.
The second line, the R is the modulus of the X vector.
Yes. R is the distance from the origin, so the modulus of the X vector. Yes. Okay. Or if you want, this is X equal to R, the distance from the origin times R. Okay. So this is the end of this half boring and half interesting story. It's a mixture of. Now, there is another operator that is useful, which is, we'll find it in a second, the L square, which is Lx square plus Ly square plus Lz square. So the module, the square of the vector. This object here, we'll see in a second. That is the crucial, one of the crucial objects of the story. In particular, I will show in a second that L square commutes with any other components. For instance, commutes with Lx, it commutes with Ly, it commutes with Lz. So in particular, it commutes with Lz. So this we will show you in a second, in 10 minutes. On the contrary, Lz and Ly do not commute, Lz and Lx do not commute, okay? But these two operators, for instance, commute. Then I can ask you, what can I do with two commuting operators? Find a basis of common eigenfunctions, right? You remember that if the two operators commute, I can find eigenfunctions which satisfy both at the same time, okay? This means that the Marxist functions of theta and phi, remember that these are differential operators that depends only on theta and phi, functions of theta and phi such that L square times this function of theta and phi is equal to some number times the function of theta and phi. Sorry, sometimes I write the phi. Okay, good. And also Lz of this function of theta and phi is equal to some other number times the function. Now, let's put things explicitly. This eigenvalue of Lz is usually denoted by m, and obviously the function does depend on this number. Okay? The eigenvalue here, well, obviously there is an h bar always. The eigenvalue here is h bar squared L plus 1, okay? And this is L appearing in this function, okay? This expression here involve what are called the spherical harmonics that you probably encounter in doing classical electromagnetism. So in some sense, there is nothing genuinely quantum about this function, okay? This comes from essentially looking at gradients and Laplacians in spherical coordinates. They automatically come out, but it's nice to see how they can actually be constructed, rather than looked with Google, constructed from this quantum reasoning that I'm trying to pursue, okay? So the next, the goal, yeah.
That's supposed to be L squared.
That's supposed to be L squared, yes. Okay? The next part of the lecture will be to show that angular momentum necessarily implies this type of numbers. Okay? So there must exist, in fact, in the orbital angular momentum case, integer. Okay? These numbers are integers. L and integer m, such there must exist eigenfunctions common to both, such that these equations are satisfied. So the spherical harmonics emerged in an automatic way somehow from the theory of quantum angular momentum. Okay, so they are not only special functions that you find in Jackson. Okay, they somehow are genuinely quantum. Okay. So let me just explain this. We want to take 2 minutes of rest because this was kind of boring.
Yeah, I thought.
Okay.
You have to press
I had to press.
the red button.
Sorry. Okay, never mind. This was boring. Okay, so it's completely 2 minutes of this. Okay, let's start again. So I have to press this one again, not this. All right, I pressed the wrong button. Okay, so the next part of the lecture is devoted to this story. Suppose that I have three operators, okay? Let me call them Jx, Jy, and Jz. And these three operators satisfy the commutation relationship that we saw a while ago for the orbital angular momentum. I call it on purposely J because I want to get rid of the understanding that this is just the orbital angular momentum of a single part. Okay? Any three operators, okay, which satisfy these rules will obey what I'm going to tell you now. Okay? So not only the L does, but the spin, which we will encounter next, also does this. And in fact, any composition of angular momenta of many particles is forced to obey this rule. Okay? So indeed, angular momenta are not just the orbital momentum of a single particle, but in principle the composition of orbital and spin angular momentum of possibly more than one particle. Okay? They will still obey the software here. So the first thing to notice is that if you divide everything by h bar, so you work with these new variables j tilde of x, okay, and the same for y and for z. Notice that you can divide everything by h bar square, and the two expressions essentially in this dimensionless variables will not involve the h bar. Is it clear? If it is not clear, divide by h bar square, h bar, you see that this is the dimensionless jx, dimensionless jy, equal to one goes with that, and the other is the dimensionless jz. So it is as if with dimensionless angular momentum, I take h bar equal to 1. Okay? So I will do that because I don't want to carry out all the h bars around the microstructure. Okay, so this is I, J, Z. Good. Next, what I want to prove to you is that if I construct J square, okay, which is by definition JX square plus JY square plus JZ square, okay, J square commutes with, say, JZ. Okay, let me just show this to you, and then you will realize that, I mean, it commutes also with JX and JY because Z is one of the three, and this knows nothing about the direction because you sum the three. So in order to prove this, you notice first that JZ square commutes with JZ, right? So here I would have JX square plus JY square plus JZ square commutated with JZ. Okay, so these two obviously commute, so you can get rid of this. So what about this? Well, this is equal to JX square JZ plus JY square JZ. Now, here you use the usual rule. I have the product of two, A, B, commutator C. Okay? So I can write it as JX, JX, commutator JY, plus JX, commutator JZ, JX. Okay? And the same for this. Okay? So notice that this is equal to X. Remember the rules. I have X, Y, Z. Okay? So X with Z is minus IJY. And X with Z is again minus IJY. So this object here is minus I JX JY plus JY JX. Okay? Then you do the similar thing here. So you have again JY, JY, JZ plus JY, JZ, JY. Okay? And then you verify that Y times Z is equal to I. So these two things here are now I, JX. And now you notice that this time I have the same object that I have there, but this time with a plus. Okay? So this with that cancels with this, and this with that cancels with that. Okay? All this calculation that I'm going to do are rather boring again. Sorry, this lecture is dominated by boring calculation, but not very difficult. Okay, you just have to suffer a little bit and do your algebra passion. Okay, good. So this object is equal to 0. 0. Okay, and if you do it with X and Y, it would be still 0. Good. Okay, now the goal is clear. Yep. Don't worry for the calculation. No. Don't copy the calculation, please. Don't copy. The result is in the notes. The calculation, either you do it yourself or it's useless. Okay? That's the rule of the calculation. You do it yourself, useful. You copy, useless. Okay, so they change dramatically. So don't, try to understand the logic. So remember that there is this A, B committed to C, okay, and then try to do it yourself. Okay, and you will see the sign beautifully canceling. You will get great satisfaction by copying the calculation by someone else. You just annoyed to death. Okay, so don't copy. Good. Now, since this is an abstract angular momentum, so not a single particle, let me just use an abstract notation for the Eigen vectors of J square and Jz. I will denote it by J and M. These are two labels. I will tell you in a second what they are. So J square and Jz are diagonalized simultaneously by this vector in the Hilbert space. M is directly the eigenvalue of Jz. Okay? While J is a label, and the value of J squared is not J, is some function of J, which I will tell you in a second what it is. Okay? So let's see better how to construct these objects J and M. To eliminate the a little bit of the very vague aspect of this thing, let me just tell you that I'm going to show to you that if the operators that I'm considering are angular moments when they satisfy this, then necessarily J has to be either integer or half integer. Half integer means 1/2 3 half by half. So twice J is integer. Okay? In both cases, the M, okay, go from say minus J plus 1 up to plus J. Okay? So they are integers or half integer of either sign, okay, and you get a ladder, okay, with steps of 1 from minus J to plus J. Okay, we'll exemplify in a while those things. Okay, so this is the goal of the next 10 minutes of discussion. Okay, to show that this is indeed the only possibility that nature allows if you have an operator doing that. Yeah.
The eigenvalue is fixed. How do you fix the FD and M?
What?
How do you fix the FD and M?
Yes. This Fj is equal to J plus 1. Okay, where J is stipulated to be integer or half integer. You see, it's this L plus 1 that we find there. I will prove this for you shortly. Okay? Good. In order to construct this story, I will need two extra operators. Okay? And these two extra operators are ladder operators. So I want to produce for you a ladder of states, okay? And I now define for you an operator that gets you up in the ladder and another operator that gets you down in the ladder. Okay, pretty much as A dagger in A in the harmonic oscillator, with a crucial difference, however, which I'll tell you in a second. That in the harmonic oscillator you can go up to infinity and you start from 0. Here you are bound in both directions. Okay. So let's see. I define, I need some space. So I define J plus equal to Jx plus I Jy. Okay. And similarly, J minus is the emission conjugate of it, so J plus dagger, which is Jx minus I Jy. I didn't specify, but obviously angular momenta are emission operators. For X and P, it's pretty obvious in general. Yeah. Okay, good. So let me just write it more compactly in the following way: plus or minus plus or minus. Okay, so there is a plus or minus I influence. Now, I told you that not only JZ commutes with J square, but also JX commutes with J square and JY. Okay, therefore, also J plus minus commutes with J square. J square, J plus minus is equal to 0. Okay, good. Now, suppose that I have some state, which I still don't know what it is, but I know that this is an eigenstate of J squared. I now apply to this state J plus. Okay, and I ask you, what is the eigenvalue of J squared for this state? Is this an eigenstate of J squared? Well, let's see. I apply J squared. Okay. Well, then since these two commutes, this is equal to J plus, J squared is equal to Fj, so it's Fj, J plus, J. Is it clear what I did? I commuted, I let this thing act, it is an eigenstate, and so I bring out the eigenvalue Fj, and therefore I discover that if I take an eigenstate of J squared and I apply J plus, I keep having an eigenstate of J squared. Okay, not necessarily the same, but somehow in the same space of eigenvalues, which might be the general. Okay, very good. Let's see what happens if I try to see what is the eigenvalue of Jz on this state. J plus, J. Okay, is it the same or not? No, it's not the same. The reason is the following, and is again one of those little boring calculations that I will try to now. So a little boring calculation will show you that Jz commutator with J plus is equal to plus J plus. Okay. Okay, which means that if I want to rewrite this object, I can use this and say Jz, J plus minus J plus Jz equal to J plus. Okay, this is what this thing is telling me. Yep. The commutator of Jz with J plus. How do I know that this is equal to this? Oh, I told you it's one of those little boring calculations, which I will try to do it for you now, but I will not do the next one. Okay. So this is equal to Jx plus I Jy. Then I do Jx equal to Jy. Jz Jy equal to minus Jx. You put the i's correctly, and you magically find that relation. So it's a really one line, but boring. Okay, so I skip it. Yeah. Yes.
What about
The z is not there. But when you take the commutator with the z, since z does not commute with x and y, unfortunately, it does commute with J plus and J minus. And in particular, the commutator with J plus is given by that. So I translate it into this expression here. And now I use it immediately. I see that Jz Jy is equal to J plus J plus Jz. So this is equal to this applied to Jm. Okay, let's see. Do you know how much Jz is when I apply to Jm? Yes, by hypothesis is m. Okay, so this term is m times that. So these two terms can be summed together and you get n plus 1 j plus a1. Okay? So you see how using the commutator, I in fact proved for you that this object here has a value of jz that is increased by 1. You see, if this was n, this object here is n plus 1. You see, this is an Eigen vector with eigenvalue n plus 1. Is it clear?
I don't see where
It comes from this thing. So let me do the thing. This is j plus n times j plus j1. Now I put this is a number, okay, and this is 1. Okay, so this is equal to m plus 1 j plus j1. Is it clear? Okay, so the m comes from here, from action of jz. Okay, fantastic. Now let's do the other little boring calculation, which is calculating z commutator j minus. So here I have the minus, you do the algebra, and you discover that it's equal to minus j minus, not plus j minus, minus j minus, which translated into formula means that if I have here the minus, I have here the minus, here I have the minus, but I have to remember that there is an extra minus in front. Okay? In other words, when I redo the algebra here, which I do now in this fast way, here there is no plus, but there is a minus in front. Okay? This is still the plus that I have there, and there is a minus. Okay? So you have again redo the calculation yourself, and you will realize that there is a crucial minus sign going on here. Okay, which is in the end giving you minus 1. Minus 1. Okay, so the plus applies to the j plus, and the minus applies to the j minus. So in other words, the j plus and j minus do exactly what I wanted to have. So if I have, say, let me write it here. If I have some m with j plus, I go to m plus 1. With j minus, I go to m minus 1. Okay? So starting from a state jm, I go to a state jm minus 1 and to a state jm plus 1 by applying j plus and j minus. Now, notice that j squared is the same. So somehow these are still with the same j. I'm not changing the overall eigenvalue fj. So the j is not changed, while the m is increased by 1 or decreased by 1. Is it clear? That's what the ladder operators do. Yeah.
Here I just see that you change the eigenvalue when you apply GC, but then you write down is change the state.
A state, remember, a state is associated to a different eigenvalue. So in other words, jz jm plus 1 is equal to m plus 1 j m plus 1. Okay, so somehow if I have changed the eigenvalue, it means that I have another state with this increased eigenvalue. Is it clear? And in the same spirit, if I have eigenvalue n minus 1, it means that there is a new state j m minus 1 associated with it. Okay? For every eigenvalue, there is an eigenstate with a corresponding label that I should change. Okay? Good. So you could keep doing it. You could keep applying J minus, keep applying J plus, okay? In principle, you might think forever, but the answer is no, not forever. And the reason for this is the following. I want to prove for you a bound now. Okay, J square. Maybe I should use this part. Let's see. J square is equal to Jx square plus Jy square plus Jz square. Okay, I can write it as Jz square plus well, I write it and then you see. Okay, you can write it in this way. If you put J plus and J minus, remember these are just plus or minus 5. You can do the algebra, okay, and you realize that it is equal to that. Now, what is the meaning of this expression? First of all, if I have something like this, Jz squared, it is a positive operator. Do you know what a positive operator is? Eigenvalues are positive. J squared is the sum of 3 positive operators. Okay, the eigenvalues cannot be negative. So this is somehow telling me that this object here, this Fj, has to be positive. Good for 0. Okay, now if I calculate, suppose that I calculate J square minus Jz, okay, on a state, J square minus Jz square on a given state. Now, how much is this? Well, this is the sum of these two objects, y square plus Jz square. Do you know why it should be positive? Let's see. Suppose that I ask you, calculate Jy square, Jm. Notice, this is not an eigenstate of Jy. It's an eigenstate of Jz and J squared. Nevertheless, this object here cannot be negative. Why? Remember, you can bring one of this J to the left, but these are Hermitian. Okay? So this is equal to Jy applied to the state Jm. Unfortunately, the notation is ugly here. Okay? Scalar product with Jy applied to the state Jm. Okay? So as you see, is the modulus square of a vector. Okay? And therefore, must be greater or equal to 0. And the same applies to Jx squared. You can also view it in this way. If you have the J minus, you can bring the J plus to the left and becomes J minus. Okay? Because they are Hermitian conjugate of each other. So the end result of this story is that this object here is bound to be non-negative because it's the sum of two positive operators. You can view it as the sum of these two or the sum of these two, whatever. But what happens then? Sorry, there is a square. If I keep increasing n, sooner or later, Jz will become very, very large, right? While J squared is fixed. I do not change J squared. So you can realize that by increasing m sufficiently far away, okay, up in the sky, this object sooner or later will become negative. Okay? You realize? Suppose that I start from some value of n. Okay? Then I can obtain another eigenvalue plus 1, plus 2, plus 3 billions. Okay, sooner or later, this jz square on the 3 billion state will be very, very large and negative. And therefore, this inequality cannot be maintained. Given the fact that j squared is fixed, you don't change that. Okay? I don't know if it takes a little bit of concentration to realize this. It's more words than formulas. Okay? So if M is sufficiently large, this thing cannot be true. Right? Therefore, there must be a final J M max. Okay, and here below there is a final M min. Okay, below this two and above this, the inequality would be violated. Okay, good. Let us try to calculate what these two things are. Okay, so suppose that I take this thing here and I try to apply. I don't know, there is something strange in this lecture. It's not going right. Things are not particularly well organized. Okay, so suppose that I take J plus and I apply to J M max. Okay, according to what we said, I should get 0. Somehow the application of this object cannot give me M max plus 1. I mean, that is what J plus would love to do. But this is the maximum. Therefore, applying this to that should just give me 0. Okay. In a similar fashion, J minus applied to this state should give me 0. Well, now, unfortunately, I just erased what I need. You can prove that J minus J plus, which remember is something which has Jx and Jy, can be written as follows: J square minus Jz square minus Jz. Remember, this is Jx square plus Jy square. And this is the usual thing that comes out when you do commutators. Okay? So boring but simple to show that this is J minus J plus. Okay, good. So since this is equal to 0, J minus J plus applied to J M max is also equal to 0, right? Because this is 0, and then I apply something to 0, I get 0. But this, on the other hand, is equal to J square minus Jz square minus Jz applied to the state, J and max. Okay? And now things are nice, because I know that this thing should be 0, but these are eigenstates. This is an eigenstate of this, right? With eigenvalue Fj minus M max square minus M max. Okay, so this object here times the state is equal to 0. How can be a state times a number equal to 0? The number has to be 0, right? So I deduced that Fj, the famous Fj here, is actually given by Fj equal to M max times M max plus 1. Okay? Clear? Well, at least in principle, okay? The algebra is boring but it is a consequence of the fact that you have to end up to some maximum value of m in the process. You cannot go on forever. Then means that there must be a 0 for j plus, and therefore you conclude that j fj has to be equal to this maximum value times maximum value plus 1. Okay, good. In the same spirit, and precisely in the same way, you must have that j minus of the minimum is also equal to 0. Okay, which means that j minus j plus, okay, sorry, here, of the minimum is also equal to 0. But then you can calculate the opposite object. Thank you. Yeah.
The fact that we keep boundaries at 0, it means that at m, the values m minus 1 and m plus 1 are discussed as in sort of symmetry.
There is a symmetry in this thing. We'll prove in a while that m max is essentially. I'll call, by the way, to stop this. Okay. I will call J. This lecture is wrong. There is some spell. Okay. I will call J this value of M max. Okay. So let me just give a name, which is this J here, small j, to this value here. By the way, in some sense, it is already used. You might say, why you are called? Okay, J here was some label, and I used Fj for the eigenvalue. Now, I just assign the label to the maximum value that you can get for M. Okay, I give J this name to this maximum value, which means that Fj is just equal to J plus 1, as promised. This is just a way of calling numbers, calling objects. But now the final piece of the story is the following. If you do the procedure with the opposite, the minimum m, which requires this, and then it requires this, you do a similar boring algebra, you discover that here there is a change from minus to plus, okay? Which means that there is a plus here, and here is a minus, the minimum. And here means that there is a min square plus a min, okay? Because of this change of sign. And here's a min, okay? So please try to revisit the thing, and you discover that the same Fj is now equal to m min times m min minus 1. Okay? Well, how can these two objects be the same? Well, there is a simple thing. M min is equal to minus n max. Okay? Which is minus j, according to my new definition of n max. Okay? You see there is a minus from here. Minus and minus, the two minus go away, and these things are perfectly well defined. So, as you said, here is the little symmetry behind this construction. If this is some value j, this is exactly minus it. And these are in steps of 1. Okay? So you go, for instance, from minus 3, minus 2, minus 1, 0, 1, 2, 3. And then you stop again. So you stop from below and from above in the symmetric fashion. Obviously, nobody so far proved for you that these are integers, right? I told you that they are in step of 1, and there is a symmetry between the minus and the plus. But you realize that there is not much freedom in that, okay? In some sense, by proceeding with integer steps, I must essentially have 2j equal to the number of integer steps that you do. Okay? So j must be either an integer or half an integer. Okay? For instance, minus 3/2 is good. Minus 1/2 plus 1/2 plus 3/2. 4 steps. Okay? Minus 1/2 is good. Minus 1/2 plus 1/2. 1 step. Okay? But minus pi is not good because minus pi plus minus pi plus 1, minus pi plus 2, you don't get to plus pi. Right? So not all minus and plus are connected by an integer number of steps. Only when j is equal to either an integer or half an integer. Okay? So, although slightly boring at times, the algebra shows unambiguously that the only possibility is to construct tower of eigenstates organized in a ladder, okay? So with the eigenvalues of jz increasing by 1, 2, with this j plus and decreasing with j minus, there is a maximum value of m, call it j, a minimum value of m, symmetrically minus j, and the eigenvalue fj is just given by j plus 1, okay? Which is, I mean, what I proposed at the beginning to show, okay? So it took a little bit of, and j has to be integer or half. It took a little bit to get to it, but the algebra is really boring but simple in the sense that the only thing that we have to use are commutators of jx, jy, jz. Okay? I never used differential equations. Okay? So for instance, I didn't construct the spherical harmonics as solutions of appropriate differential operator in theta and phi. I didn't, right? I just used formal algebraic relationships, which, however, allowed me to conclude that the possible eigenvalues of j squared and of jz should be given by these numbers. Okay, not all possibilities are allowed. So we are pretty tired. I am tired for sure. Let me just give you. No, maybe I should just. No, I finish a couple of things, but then we stop. So far, you might get the impression that if I apply j plus to an eigenstate jm, let's see. What we know so far is that I get j, I get n plus 1. That's it. In principle, I didn't tell you what was the normalization constant. There could be here some constant in front, right? Because I always require that the states are normalized to 1. And the constant here in front is, I'll write for you, and then we describe how you get to that. It's equal to minus m plus 1. How can you get it? Simple. Look at this object. Okay? So if I take j plus jm, okay, and then I take the scalar product with itself, which means j minus jm. Okay, I put it on the left. Okay. Now I realize that this object here is unfortunately the other one. So it was this minus, plus, minus. Okay? This one. So this object here is in fact equal to j squared, which is j plus 1, minus m squared minus m, okay? Which is equal to j plus 1 minus m plus 1. Okay? So you realize that whatever is this object here, the constant in front must be such that if I take the square of it, I get exactly this, because this object here is supposed to be normal. Okay? So it is the square root of this quantity that you have to put there in order to make the two equality correct. Is it clear? And in the same spirit, if I apply j minus, again, I do not simply obtain m minus 1, but I really obtain a square root in front with an m minus 1 there. Okay? Again, this has to be verified by some annoying algorithm. Okay, so next time I will show how, using this general theory, you can construct spherical harmonics. Okay, so you don't have to rely to Jackson. You can construct actually the spherical harmonics by hand, essentially, using the theory and the form of the differential operator that we derived for the orbital angular momentum in the first part of the lecture. All right, so I think we stop here because this is really a terrible tour de force of partly boring calculations.